Gireeja, the VGA cable is actually the HDMI 2 plate. So it'll be between HDMI 1 and 2.
Okay, time to get started. Welcome back after your long weekend. I hope you all had a great time. So there was no section yesterday because Monday was a holiday, which means that there is going to be, there's always section Monday and Wednesday, so make sure you go to section on Wednesday because, there's going to be material covered in Wednesday that will be helpful for you on the homework. Which reminds me that homework 1 self-grades will be due tonight at midnight. Homework 2 has been released. I hope all of you have seen it. I hope all of you have started to try the problems. I think it's a great homework. I think it's full of kind of fun problems. But I really encourage you to start the homework early. Do not start the homework Friday morning. There is, the reason that we have these weekly cycles is so that you have some time to start the homework, think about it on your own. Then we have office hours. Then we have homework parties. So, first you get some time to try it on your own. Then you get to ask, your peers or your TAs or your instructors about things that might be confusing. Then you have homework party to actually sit down together and finalize up your solutions. The schedule is, planned out in a way such that you can gradually make progress on your homework. So please start the homework early. Don't wait until the last minute. Other point, yes. Given last week was the first week of discussion, and as we saw that there was some kind of imbalance in the number of people that were attending every discussion. Some discussions were really packed. Other discussions didn't have as many people. So for this, we have designated new sections as sections for freshmen, as well as sections for people who have a background in linear algebra. So there are new orange and blue sections on the website. Please, check if you're in a section that has been having an overwhelming number of people in the section. Switch to another section, you'll get more attention. And we've tried to put these at times that were in the highest demand. So, any questions about any of this? All good? Okay. Go to section tomorrow. Again, reminder, you have to go to section on Monday and on Wednesday. There's a lot of questions on Piazza. Both days are required. There's different material covered. You will need this to complete the homework. Okay. So with this, let's get started about today. So today we're going to cover a bunch of different concepts that are really important conceptually when you're thinking about linear systems. And we're going to start thinking about, systems of linear equations as representing things that are systems in the real world. And homework 2 is really all about this. You're looking at different kinds of linear systems in the real world, and you're trying to think about how to model them, how can we use the tools of linear algebra that we're learning to actually have practical impact in the applications that you're building. So for this, we're going to talk about a few concepts. We're going to talk about span, we're going to talk about linear dependence and independence, and we'll see, how linear dependence and independence relates to solutions for systems of linear equations, which is something that we've been talking about for a while. And then we'll start to think about also some different perspectives on modeling and see how we can think of matrix vector multiplication as we already know. It's a way of representing a system of linear equations. We talked about this column perspective last time in class, and now we'll talk also about a state transition perspective, which is, for example, there's a problem on your homework that is trying to capture exactly how you can approximate nonlinear systems as linear systems. For example, this self-driving car problem. And if we have time, we'll go into matrix multiplication. If we don't have time, we'll just cover that next class. So last time in class, we talked about the column perspective on matrix vector multiplication, right? Matrix vector multiplication. And in particular, we saw the following. We saw that if A is the following matrix, A11, A21, A22, A23, A31, A32, A33. We started thinking about this as stacks of columns, right? Instead of just a block of numbers. So we called the first column vector A1, we called the second column vector A2, and we called the third column vector A3. And then, if we have this vector x is equal to x1, x2, x3, we saw that ax, what is this equal to in the column perspective? People call it out. I can write this as a linear combination of the columns of the matrix A, right? So, what is the weight that I want to have for A1? x1, x1 A1 plus x2 A2 plus x3 A3, right? We have this linear combination perspective. And we also talked about how to interpret these columns, right? What was our interpretation of these columns? We said that these columns of A are basically representing the sensitivity, right? These are the sensitivity of each experiment to the variable x1. And of course, our original perspective was that each of the rows was each experiment, right? So for example, in the tomography case, each row is like every time we shine light through the object, right? But what the sensitivity is capturing is how every pixel in the image actually affects your measurement. So basically we had this, just to remind everyone, if we have an object, let's say some guy, maybe with some cool hair, that we're trying to measure something about this person. We do an experiment, and we're going to represent what we don't know as this x. The experiment somehow transforms x and gives us our measurement. So we measure b, and what we call the transformation that the experiment is doing, we can represent this by this matrix vector multiplication, right? Ax equal to b. And we've been talking a lot about how to solve these kinds of systems. So now, given this column perspective, I have a question. What happens if, for example, this vector a1 is the 0 vector? Take a minute and talk to your neighbor and think about what can we say if a1 actually turns out to be the 0 vector. What does it tell us about our experiment? Make sure no one's left out. Make sure everyone has someone to talk to. Okay, let's come back together. So, anyone want to volunteer what they thought about, what happens when a1 is 0? Yeah. Great, right? What did he say? He said that if a1 is 0, it means that you actually didn't get any measurements about the variable x1, right? And so, if I give you a lot of measurements about the variable x2, and I ask you to find out what is x1, what are you going to tell me? You're going to tell me that you can't do that. You don't have any measurements, right? So this is exactly what we're going to try and understand further in this lecture. So a1 equal to 0 is a special situation where, intuitively you feel like if I want to solve for x1, x2, all the way up to xn, but none of my measurements involve the variable x1 at all, probably I'm not going to be able to figure out x1, right? I never measured it. So this is one way in which we can see how a system of linear equations might not be solvable. This is related to this idea of the linear dependence of the different columns, and this is what we're going to try and understand in the rest of this lecture. So before we go into that, so if a1 is equal to 0, basically we don't have any information about x1. So I want to introduce now a little bit of definitions and terminology and jargon that will help us going forward. First, I want to introduce this notion of a span. So what is the span? So I want to think of a span of a set of vectors. So the span of vectors a1, a2, all the way up to an. I'm going to define this as the set of all vectors that can be written as a linear combination of a1, a2, A-N. And if I wanted to write this kind of mathematically, I wrote this out in English, I can write this the following way. And I'm going to introduce some notation here. So, ask questions if it doesn't make sense. So I'm going to write this as the following set. And I'm going to use this notation called the sigma notation for the sum. So this is the sum I going from 1 to n, ci, ai, such that ci are in the real numbers. So, what does this notation mean? This means that I'm taking all indices going from 1 to n and adding up all of the corresponding elements. So I have C1, plus C2, A2, plus all the way up to Cn, An. So it's just a shorthand notation so that I don't have to keep writing these long summations out. Any questions on what this notation means? Great. And then we are using this other symbol here. This just means belongs. And this just means the real numbers. So it's just another way of saying linear combination. Do you see that? It's just a shorthand way of writing out a linear combination of these vectors of A1, A2, An. Mathematics is often about, being concise, or as other people might call it, being lazy. So now that we have this definition, so let's try and kind of play with it and understand with it. And keep in mind, right, we've been thinking a lot about linear combinations of different vectors, right? So we're going to want to try and connect this quite soon to our systems of linear equations and our matrix vector multiplication. But before we do that, let's just try to do some examples. So now, oops, can you see this? You can see that. So let's now consider the following example. Let's say my set of vectors is 1, 1. What is the span of 1, 1? Okay, let me draw out 1, 1. I have my x-axis and my y-axis. This is 1, this is 1. So let's say this is A1. What is the span of this vector? Yes, question? The answer is the line y equals x, yes. So what is he saying? He's saying that, well, if I take a linear combination of one vector, right, what does that mean? Just means scaling the vector, right? So if I scale it in the positive direction, I can get basically anywhere here. And if I scale it in the negative direction, I can get anywhere here. So any point on this line, any vector on this line, is basically in the span of this vector. Everyone on board? Any questions about that? Good. So now let's take another question. For example, what is the span of, let's see. Let's take 1, 1 and minus 2, 1. So what is 1, 1? We just drew it out. We have 1, 1 right here. Let's draw this with a different color. So then we have minus 2, 1. So let's see. Let's try and figure out if different points are in the span of A1 and A2. How about if I pick some point here? Is this point, is this vector in the span of A1 and A2? How would I get to this point? How would I get to this vector B, let's say? Yeah?
Scale A2 by something greater than 1 a little bit, and scale A1 by something greater than 1 a little bit, and add them together.
Okay, so it's kind of like you kind of walk along A1 as far as you can, and then you walk till you get A2, right? That's kind of the solution that you're suggesting. So you kind of go like this till you get to a point that you're parallel to this. Then maybe you can do that to actually get to this vector B, right? So where would you use a concept such as span? Give me 1 second. So think about the following. Say you're trying to, figure out the motion of some kind of robotic vehicle, right? You know that a robotic vehicle cannot always move in every single direction that you want it to move. Like, for example, if you think about your car cannot move horizontally, right? It can go in certain directions and not in other directions. This is not going to exactly explain to you the motion of a car, but it's just an example to kind of get you to think about this. But now, if you're thinking about, like, for example, the motion of a robotic arm, if you know that your object or your arm can translate along, say, vector A1 and A2, then you can get it to be in any point that can be a linear combination of A1 and A2. If you know that your robot can move in this direction and this direction as much as it wants, then you can move in this direction and then move in the other direction till you get to the point that you want. So what we see here is that for this particular set of A1 and A2, what we have is that our span is actually the entire 2D plane, right? Or we can also write this as R2. R2 just means all pairs of real numbers. Yeah, so there's a question at the back first. We're going to get exactly to that in a second. Yeah?
So the earlier example, how would we, like, if we were asked what is the span, and we just say, like, x1
What is the span of, like, x1 and x2, or what do you mean?
Yeah, for, like, the first example, span of just the vector 1.
Uh-huh.
If we were asked, like, what is the span of that vector,
Well, you would actually write it as a set of vectors. So the span of this would be the set of all vectors, C times 1, 1, such that C is in R. So another way to think about it is the line y equals x, but if you're going to write it in vector notation, since we're defining it as a set of vectors, you would actually write it as a set of vectors. Is that clear? Yeah. Okay. So now, what about the following case? What is the span of 1, 1? And I'm just going to, like, start writing this in the lazy notation. Just write these as a matrix where I'm now interested in the span of the columns of this matrix A, right? So I'm thinking about this guy is a vector and this guy is a vector in the usual way that we've been thinking about the columns of matrices. What about the span of this guy? Someone at the back who hasn't answered yet. Yeah. Yeah, what she's saying is that they're just kind of multiples of each other, right? So if I draw these out, I have my 1, 1 vector here. I have my minus 2 vector here. And so, what is the span that I'm going to get? I'm going to get the same line, right? I'm going to get exactly this as the span. So here we had 2 vectors, and we managed to get the entire plane. Here we had 2 vectors, but somehow we didn't. And the question is, what is really going on? And how do we understand, well, can we get to any point B? And so if I wanted to get to any point B using this set of vectors, right, I want to say, well, can I write a linear combination of these vectors that will give me the vector B? And how do I write a linear combination of these vectors in the new notation that we've learned? Louder? So you can write it as C1 times 1, 1 plus C2 times minus 2, minus 2, right? But we learned another notation for linear combinations of vectors. Jogging someone's memory? That's another way of writing it. But what about, can you write it using a matrix? Can you write it using this matrix? How would you write it using this matrix? People over here. Someone else, yeah. Yeah, right? What did we say? We can write matrix vector multiplication as a linear combination of the column vectors. So if this is a column vector and this is a column vector, then what does this represent? This is exactly equal to this, right? Is everyone clear on that? Yeah? I'm sorry? Oh, in this case, yeah, the way I set it up, you're right. No, this is fine. Yeah, this is correct. Yeah, let's write this out, right? 1 minus 2, 1 minus 2, C1, C2 is equal to, let's say, B1, B2. So what does this get? 1 times C1 minus 2C2 is equal to B1. And then 1 times C1 minus 2 times C2 is equal to B2. So if this is equal to B1, B2, I get exactly the same equations. And again, remember, what does this mean? This is the coefficient of this variable. This is the coefficient of this variable. Coefficient of this variable, coefficient of this variable. So when we write it out in this form, right, what do you see from what you've learned about Gaussian elimination? Are you expecting to be able to solve this system of linear equations and get a unique solution? No, right? You see it immediately when you write it out as this matrix that, hey, we know that we're going to get a row of zeros here. We know that this isn't going to happen. And this is exactly connected to the reason why these two vectors cannot span all of the 2D plane. Is that connection becoming apparent to people? Okay. So now, what I want to do is basically use this to explore another concept. So we know basically that now AX equal to B. This is something that we know we've thought about a lot in this class already. But now we can think about another interpretation of this, right? Does B belong to the span of columns of A? How is this question related to does AX equal to B have solutions? It's basically the same question, right? We're just rewriting it in a different way. Because if AX equal to B has a solution, that means that there is some linear combination by which I can take the columns of A and achieve B and arrive at B, right? So we can think about this as either linear combinations of this, of the columns of A, which gives us this interpretation for the span, or we can think about it as just a system of equations that we want to solve. And these are two ways of thinking about the same thing that we're going to go back and forth between. Is this clear to everyone? Any questions about this? Okay, great. And just as a piece of notation, when you have AX equal to 0. What is the solution of ax equal to 0? X equal to 0, right? X equal to 0 is always a solution of ax equal to 0. If I want to get the 0 vector, if I wanted to get all zeros here, I can just put all zeros here. So when you have an equation of this kind and you solve for x, this is often called a homogeneous solution. But when you solve for a system such as ax equal to b, this is often called a particular solution. This is just some terminology so that in case you come across it somewhere else, you'll know what they're talking about. Yeah, question, white sweatshirt. If we were to, so this is an example with 2 by 2 vectors. The question was, what do you do for n by n vectors? Is that correct? So if you had if you're thinking of n length vectors, then you would write out actually length n vectors. It wouldn't be a 2 by 2 vector. So in this case, we happen to have the same dimension of the vector as the number of vectors. But I could have 3 2 by 2 vectors. I could give you 1 1, 2 2, and 1 2. And I could say find the span of these guys. So I can give you more vectors than there is dimensions. I could give you more dimensions than there are vectors. So for example, if I say what is the span of 1 2 3? That's one vector, but it's a 3-dimensional vector. So there's no need for the number of vectors to be exactly the same as the number of dimensions. But when we come to ideas around basis, which we'll come to in a couple of lectures, we will start to think about, the dimensionality and the number of vectors that we're thinking about while considering the span. But that's thinking forward a couple of lectures. So now with this, I wanted to now think about yet another definition, because what we're trying to see is, basically, what is this relationship, right? How do we understand when we can achieve a certain, when can we achieve a certain vector as a linear combination and when can we not, given a certain set of vectors? So let me now make another definition. Linear dependence. So when we looked at this example right here, basically what was pointed out is that, you can scale one of the vectors. You can scale 1 1 to get minus 2 2. So the directions that these vectors are going in are not that different. And they're actually exactly the same, which means that, and this is somehow related to the fact that we cannot, get to any point in the 2D plane using these two vectors. So we want to formalize this, and we want to say that a set of vectors, A1, A2, all the way up to AN, are linearly dependent if one of the vectors can be written as a linear combination of the rest of the vectors. Okay. So if we wanted to write this out in, a little bit more mathematical notation, we could say there exists an index j such that the vector aj can be written as a linear combination of all of the remaining vectors for I going from 1 to n, except I don't want I to be equal to j, right? Because I can always write a vector as a linear combination of itself. So here I want to exclude all cases. I don't want to allow I to be equal to j. So I'm just writing what I said above in this notation. Is this notation clear to everyone? Okay. So now, let's start with the trivial example. What about a1 equal to 1, 1, and a2 equal to minus 2, minus 2? Are these vectors linearly dependent? Yes? Why are they linearly dependent? a2 is equal to minus 2 times 1, 1. What about another example of linearly dependent vectors? Someone? Can anyone give me an example of linearly dependent vectors? 1, 0, and 2, 0. Again. So a2 is equal to 2 times a1. Good. So any questions about this? Okay. What about the following set? a1 equal to 1, 1. a2 is equal to 2, 1. And a3 is equal to 3, 1. Is this set linearly dependent? Yes. Maybe, maybe not. How would you figure out if this set is linearly dependent? Someone else. Someone who hasn't answered. Okay.
It's guaranteed to be linearly dependent since there's 3 vectors and it's only in R2.
The solution is it's guaranteed to be linearly dependent since there's 3 vectors and it's only in R2. This is almost correct, but could I somehow come up with a trick solution that would not have that situation happen? Like if I gave you a bunch of 0 vectors? So you're right, except you have to be slightly careful when you make these statements, right? You're basically right, though. Okay, so here again, we see that this is linearly dependent. We're skipping some steps here. But if it's not clear to you why this is linearly dependent, please come talk to me in office hours or try and work it out on your own. But basically, if we can write A3 as sum C1 times A1 plus C2 times A2, then we're going to be able to say that these are linearly dependent. And everyone knows how to find such C1 and C2, right? What is the procedure that we would use to find such C1 and C2? Gaussian elimination. So everyone can go and check that these are actually linearly dependent. Okay. So it turns out that we can actually define linear dependence in a second way. So we can also have a second definition for linear dependence. And this definition is the following. We say a set of vectors a1 to an is linearly dependent if there exist constants ci, not all 0. This is going to be very important. Such that you can write ci ai equal to the 0 vector. I is going from 1 to n. So this definition is very similar to the earlier definition. Can you see both definitions? So take a minute and talk to your neighbor and think about why I'm saying that these two definitions are equivalent. And think in particular about what does this, CI not all zero, what role is that playing? Just, this is something that is subtle, but take a minute, talk to your neighbor, think about what these two definitions are saying, and try to explain to your neighbor why you think these two definitions are equivalent. Go for it. Okay. So how many people feel like they can justify why these two definitions are equivalent? I'm not going to call on you. Just how many people feel that they can justify this? To their neighbor, quietly, secretly, without ever talking to me. How many people are a little bit confused? Okay, that's fair. So let's talk a little bit about it. This is written out very carefully in the notes, and I'm not going to have the time to fully go through it. If we have time, we'll do it at the end of lecture. But basically, if you think about this formula, right? If I have the following, what happens if I take this and I transform it in the following way? Can I rewrite this equation as 0 is equal to sigma I equal to 1 to n, I not equal to j, ci ai, minus aj. Does this imply this?
Yes.
How many people are on the board? Especially the people that were like a little bit confused. So when you have this, can I then write this as further equal to sigma I equal to 1 to n ci ai, where I define cj equal to minus 1. So I'm saying when I'm taking these linear combinations, what is the weight that I'm going to put on aj? Minus 1. I'm going to say that let's do this. So this implies this. And so, what do we have here? Let's look at all of these. This is a linear combination of all of the vectors. Are all of these weights, the C1, C2, Cn, are they all 0? No. Why are they not all 0? People at the back, why are they not all 0? Yeah. I just said Cj is equal to -1, right? So, do I see that basically I have the following condition that is being satisfied? So if this condition is satisfied, I can satisfy this condition. So are the people who were confused, does this kind of make sense? as to what we're doing? There's a second part that we haven't discussed. What if you start with definition 2? Can you get back definition 1? I'll leave this as an exercise. It's in the notes. If it doesn't make sense, come talk to me afterwards. So we have these two ways of characterizing linear dependence and linear dependence. But now it really is asking the questions, right? We're really tempted to ask the question, well, what is the opposite of linear dependence? Can we talk about linearly independent vectors? What we're seeing is that when things are linearly dependent, we can write one vector as a linear combination of the others. What about linear independence? So a set of vectors, A1, A2, all the way up to AN, is linearly independent if they are not linearly dependent. It's a really simple definition. But what does this mean mathematically? Again, if we wanted to write this out mathematically, it means that if you tried to claim to me, let's say we were having a discussion about whether a given set is linearly dependent or linearly independent. And you said, well, I think they're linearly dependent because here is a linear combination such that all of this linear combination of the vectors is equal to 0. So if I give you some C1, A1 plus C2, A2 plus Cn, An equal to 0, if you were to give me such a set, then I would say that actually you're going to have the following situation. You're going to have C1 equal to C2 equal to Cn equal to exactly 0. So if you were to find a linear combination of these vectors that led to the 0 vector, then what you're going to get is actually that every single one of those weighting factors is exactly 0. You cannot have a non-trivial linear combination which gives you the 0 vector. Is that clear? Any questions? Okay, great. So why are we studying all of these things, right? Why do we care about linear dependence, linear independence? It's because there's a lot of interesting applications that actually use this. So one of the problems on the homework is about encoding for communication. So when you're thinking about, your cell phone transmitting, whatever text messages you're sending, or transmitting your voice phone call through an antenna wirelessly to the next phone, what is used in transmitting this information is called a communication code. Question? No. Yeah. What is used in this kind of transmission is called a communication code. And we're not going to have enough time to, go into all of the details on communication codes in this class. If you're really interested in this stuff, you can go on and take classes in information theory like 229A or coding theory 229B. Before this, you could take a class like 126, which will help you prepare for this. But what we're going to talk about is a little bit of a hint of what these ideas are. And this is actually one of the problems on the homework, where you have Alice trying to communicate some pieces of information to Bob. And encoding and decoding actually very critically uses a lot of these ideas of span, linear dependence, linear independence. When you're trying to figure out if a piece of information that has been transmitted is corrupted or not, you will often use the structure of the code to be able to decode it. So I'm not going to be able to talk about all of this in a lot of detail, but I just wanted to kind of talk a little bit about for 5 minutes about the homework problem that you guys are going to be doing. And for that, I wanted to just introduce one piece of notation, which is the transpose. So if I have a vector x, which is equal to x1, x2, let's say, xn, x transpose is basically writing the vector horizontally, x1, x2, all the way up to xn. This transpose is denoted by this little t that's up here. And if I take the transpose of this vector, if I take the transpose of a horizontal vector, of a row vector, I would get a column vector. So it's just a notation that allows us to go between writing vectors horizontally versus writing vectors vertically. Most of the time in this class, we'll be thinking about vertical vectors. But it's useful sometimes to be thinking about horizontal vectors. So what is happening in this homework problem that you have, right? Alice is trying to send something to Bob. And she's trying to send a vector, right? She's trying to send a vector, let's call it A1. And what she's doing in sending this is she's saying, I'm going to send a linear combination of the components of this vector A1. So now, using this transpose, I can actually write, let's say I want to take, let's say A1 is A11, A21, A31. I can write, let's say I want to take this linear combination, beta 1, A11 plus beta 2, A21 plus beta 3, A31. I can write this using this transpose notation as, just write beta 1, beta 2, beta 3 times A11, A21, A31. And if I define the vector beta as beta 1, beta 2, beta 3, I can write this as beta transpose A1. Is this clear to everyone? So now, if Alice is going to try and send different linear combinations, and she's going to keep getting many chances to send these linear combinations, she could choose these different vectors, betas, right? And I could choose, if I choose beta 1, beta 2, beta 3 the first time, what should I choose the second time? Should I choose the same beta 1, beta 2, beta 3 again? Everyone's saying no, but why? I just want you to think about this. This is very related to the homework, and I'm not going to actually discuss the solution to the homework here. But what I want you to think about is, in the tomography example, the first day of lecture, when we took these different measurements, right? We took 2 horizontal measurements and we took 2 vertical measurements. And then we said, wait, we don't like the 4th vertical measurement. We don't like it because it is redundant, right? And so somehow if Alice is trying to transmit information to Bob, does she want to transmit redundant information? No, not really, right? So what she wants to do is transmit non-redundant information. And what the homework is going to try and do is explore different ways of doing this and think about how efficiently you can actually transmit information. But what we're looking at here, when we're thinking about redundancy in equations, what matters in terms of redundancy of equations? It's these rows of the matrix, right? When I think about beta 1, beta 2, beta 3, and if I think about my next transmission, which might be beta 4, beta 5, beta 6, we're thinking about the relationship between these guys. So I'm not going to say much more about that because I do want you to actually enjoy the homework, but I just want you to say that, what we're talking about today is not going to directly, this is not going to solve the homework, but conceptually all of these ideas are intertwined. So this brings us to now, why should we study really this kind of linear dependence and linear independence? Why study linear dependence? So we had this situation where we had this person, and they went through the experiment, and they came out as a measurement. And so we have this vector x, and we have the experiment which transforms them to ax, which gives us this b, right? And remember in the first setup where we saw that, first day where we saw that if we took measurements this way, this way, this way, and this way, we ended up with a matrix with redundant rows, remember? But now what we've also seen is we have this way of thinking about the columns of the matrix, right? What is linear dependence and linear independence talking about? Linear dependence and linear independence is talking about the columns of the matrix. When we were thinking about measurements here, we were thinking about the rows of the matrix. And so what we're going to talk about now is we're actually going to say formally how these two perspectives are related to each other. And which brings us to a theorem that we're actually going to prove, which says that theorem, if the columns of A are linearly dependent, then AX equal to B does not have a unique solution. So when we think about AX equal to B not having a unique solution, what do we usually think about? What have we thought about it as? We thought about it as this Gaussian elimination, right? We add and subtract these rows and we take these linear combinations and so on and so forth. And when we think about linear dependence of the columns of A, what are we thinking about? We're thinking about these columns, right? We're thinking this vertical perspective versus this horizontal perspective on Gaussian elimination. And the question is, can we actually formally connect these two ways so that when I give you a matrix, you have multiple different techniques by which you can evaluate whether your experiment is a good one, right? One way of evaluating whether your way of shining light is a good one is by doing Gaussian elimination. But what we're going to do here is through this column perspective, develop a second way of evaluating whether your experiment is a good one. So if I wanted to show that a system of equations does not have a unique solution, what are different ways that you might actually be able to show something like this? If I wanted to prove to you that some equation has a non-unique solution, what would you do? What if I gave you a bunch of examples and I said, well, here's a solution. X equal to 1 is a solution. X equal to 2 is also a solution. X equal to 3 is also a solution. Would this be a valid way of proving to you that there is not a unique solution? That seems like a reasonable strategy, right? If you want to say there's not only one solution, give a bucket full of solutions. And this is exactly the strategy that we're going to try and take to be able to actually prove this. So for this proof, let's write down first. Whenever you see a proof, and part of the things that, this class is trying to teach you is how do you approach something where you're said, well, prove the following claim, prove the following statement. Write down what you know about the problem and see how that can get you where you need to go. So what do we know about this problem? The problem is telling us exactly one thing. It's telling us that the columns of A are linearly dependent, right? So what does that mean? Let's write that down. So if the columns of A are linearly dependent, what does it mean? We can write one of the vectors, column vectors, AJ, there exists. And just because you might see this notation, this symbol, this like inverted F, means there exists, such that this is equal to this. I equal to 1 to n, I not equal to j, c I a I. Right, if I tell you that the columns of A are linearly dependent, does everyone agree that this is true just from the definition? Okay, so let's start to play with this, right? Let's start to see how we can kind of understand this equation. So I'm going to ask you a question. Can you find me a way of writing AJ? So this is the left-hand side of the equation. As A times some vector x. Can you find x such that A times x is equal to exactly AJ? Take a minute and talk to your neighbor and see if you can find this x. So remember, what is A? A is made up of the columns A1, A2, AN. So another trick to do when you're trying to solve something, write down what you know. A is equal to A1, A2, AN. So if I wanted to solve A times some x equal to AJ, what should that x be? I really, really encourage you to talk to someone. Don't let anyone feel left out. Find a friend. You guys don't seem to have many friends around here, so find someone and make a new friend. Introduce yourselves. At the back too, you guys, make some friends. How many people think they have an X? How many people, I'm not going to call on you. How many people need a little bit more time? So, I had like 5 hands raised. No one needs more time and you don't have an X? How many people think they have an X again? I'm not going to call on you. Okay. So it seems like a lot of people have a sense. So, anyone want to share how they went about trying to get this X? Someone else. Someone else who hasn't answered. Yeah, orange. Very interesting, right? What was his solution? He said, choose this x. Let's call this vector z. He said, choose z to be C1, C2, Cj minus 1, 0, Cj plus 1, Cn. Is this a correct representation of your solution? So, what he's saying is that when you take A times Z, you get, based on our definition, right, you get C1, A1, plus C2, A2, plus Cn, An. But what do we know this is equal to? This is equal to the summation, and what does this summation equal? This is exactly equal to Aj. Let's call this star by star. Right? Does everyone see how this vector actually works? How many people came up with a different solution? Are there any other solutions that we could try? Someone who hasn't answered. Yeah.
0, 0, 0, blah, 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 CJ, blah, 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 0, 0, 0.
CJ or? Right. So what if now I try the following vector? Y is equal to 0, 0, 0, 1, 0, 0, 0. Where dot, dot, dot. This is at the jth position. So everyone take a minute and write out A times Y. Really take a minute, talk to your neighbor, see what A times Y is. So what happens when I take A times Y, right? I basically have this matrix A times this 0, 0, 0, 1, 0. So when I take my perspective of A times a vector as the linear combination of the columns, what is the weight on the first column? 0. Weight on the second column. What is the only non-zero what is the only column with a non-zero weight? Aj, right? So this is exactly equal to this vector Aj. Do we see this? Now the question is, are these two vectors equal? Are Z and Y identical vectors? They're different, right? How do we know that they're different? Well, they're different at the jth position. Vector Z has a 0 at the jth position, and vector Y has a 1 at the jth position. So what does that mean if I take vector Z minus Y? What is vector Z minus Y? Is it equal to 0? This is not equal to 0. So now, but what happens if I take AZ minus AY? What is this equal to? This is equal to 0. Right? So I can write this as A times Z minus Y is equal to 0. Where Z minus Y is a non-zero vector. Okay, so I have this kind of weird situation here where I have A times something that is a non-zero vector giving me actually the 0 vector. And this is something that we're going to come back to in this class, but it's something that we don't see actually when we're doing scalar multiplication, right? If you have scalars and you have a times something is 0, where a is a scalar, then, a times x equal to 0, then x had better be equal to 0 if a is not equal to 0. But this is not the case in this vector setup. We've just shown here, we've shown an example. So now, remember, what did we want to prove? We started by saying, let's explore what we understand when we're thinking about, we want to prove this theorem. We started by exploring linear dependence. And we want to say, if the columns are linearly dependent, then ax equal to b does not have a unique solution. So, let's now think about coming back to the proof. What do we want to show? We want to show that there's a bag of solutions, right? There's not just one solution. There's many, many, many solutions. So let's say now, W is a solution. So A times W equal to B. Right, let's say this W is a solution. Can we somehow use what we've derived from this linear dependence to construct another solution? What happens if I do the following? If I take A times W plus A times Z minus Y. This is equal to A times W plus Z minus Y. And what is this equal to? Just A times W is equal to B, right? And is this guy the same as the vector W? No. Why is it not the same as the vector W? Because Z minus Y is a non-zero vector. So this guy is not equal to W. So now we have two solutions. We said, what if there's only one solution? But I produced a second one. Could you produce a third one? What if I, instead of saying A times Z minus Y, I said A times 2Z minus Y? What would happen then? Would I get another solution? And I'd have another vector. Could I produce an infinite number of such solutions? So now basically what you're saying is that if you give me one solution, I will produce an infinite number of solutions. So what have you just proved? You've proved that if these columns are linearly dependent, you can actually generate an infinite number of solutions from even just given one solution. So you cannot possibly have a unique solution. Yeah, question? Sorry, repeat the question? Z and Y are solutions. So the question is, good question, Z and Y, isn't the fact that Z and Y are solutions enough to prove that there isn't a unique solution? Z and Y are solutions to the equation AX equal to AJ. Z and Y are solutions to this equation. But the equation that we're trying to solve is the following, right? This equation that we're trying to solve is AX equal to B. Right? So we use the fact that there are two solutions to the pink equation to find multiple solutions to the purple equation. Is that clear? Good question. Okay. So now we have a little bit of time. It turns out that we can also prove something in the reverse direction. So we can also prove a following theorem, which is in the notes and I'm not going to do in class. If AX equal to B has an infinite number of solutions, then the columns of A are linearly dependent. And I'll give you a quick hint about how to do this. If you have AX equal to B and AY equal to B, you can get A times X minus Y equal to 0. And you can play with this again to try and prove this theorem. But I'm not going to actually prove it out to you, and think of it as it just builds on it's very similar to the ideas that we used in the other direction. So think about it, talk to your TAs or me. If you can't figure it out, read it in the notes. So basically, we have these two theorems give us a way of going back and forth between linear dependence of the columns of A and the number of solutions we have. So we now have this row perspective on thinking about when equations are redundant and we can't solve the system, and we have a column perspective. And you can formalize this row relationship between redundancy on the rows and redundancy on the columns. I think there was a question on Piazza that was asked about this. So this is also something we can talk about. Come to office hours if you're interested, and we'll learn more about this in 16B when we get to that point. But in the last 5 to 6 minutes, actually I have 6 minutes, I want to talk about something slightly different. And I want to talk about the following setup. I want to talk about another interpretation of matrix vector product. As a transformation of states. And if you see the self-driving car problem on the homework, as well as the imaging problem on the homework, are both talking about this same perspective on matrix vector multiplication. Take a vector and transform it into something else. Think about the vector as representing the state of the system. What do we mean by the state of the system? Like, how does the system look like right now? What are the characteristics? So for a self-driving car, this might be, what is the position? What is the velocity? What is the acceleration of the car? These are things that might constitute the state. But here I want to talk about this in the context of a slightly even simpler example. I want to talk about this in the context of flows of water or a certain kind of liquid, or you can think about it as a flow of basically anything. And really, again, this is coming back to the aesthetic of 16. We're going to talk about a very simple example, which is not entirely realistic, but we're going to try and understand things in this simple example so that you can then build it to these more realistic examples, for example, in your homework. So let's say I have these 3, cities. Let's call them city A, city B, and city C. And each of these has a water reservoir. But these cities all share water, and, at every time unit, there's kind of some level of pumping that is pumping water from one water reservoir to another. So, for example, maybe, when the pumps run, half of the water in A goes to B, half of the water in B goes to C, and half of the water, or let's say a third of the water in C, goes to A. And further, let's say maybe from B, when the pumps run, there's an amount of water that is transferred back, and a sixth of the water is transferred back. So if a sixth of the water is leaving B to go to A, and half of the water is leaving B to go to C, how much water is going to remain in B? Well, that's going to be exactly a third of the water, because, the total amount of water, the fraction of water has to be exactly equal to 1. So a third plus a half plus a sixth is equal to 1. If a half of the water is leaving A, how much water must remain in A? A half. And if a third of the water is leaving C, nothing is going from C to B, how much water must remain in C? 2/3 of water must remain in C, right? So now, can we try and think about this system as, can we represent this using the ways that we've been representing other systems as a system of linear equations? So if we think about this, let's look basically at what is happening to the water in let's say A. If we want to figure out the water that is in A after the pumps have run once. So let's look at SA, which is the water in A, at time 2. Well, I'm going to look at what do you need to know to understand the water in A at time 2. I've told you how the water is moving. But if I want you to now understand what is happening to the water at time 2, what else do you need to know? The water at time 1, right? If I don't tell you if the tank was completely empty or filled to the brim at time 1, how are you going to find out what the water was like at time 2? So if I want to find out the state of the system at time 2, I need to tell you what the state of the system at time 1 was. So I'm going to write this, let's say, as a function of the water at time 1 in A, the water at time 1 in tank B, and the water at time 1 in tank C. And so what do we have? We have half of the water in A stays in A, plus how much of the water in B goes to A? We have 1/6 of the water. And how much of the water in C goes to A? 1/3. So we have this 1/3 of the water. What about SB at time 2? SB at time 2 is going to be 1/2 of SA at time 1 plus 1/3 of SB at time 1. Plus, is there any water from going from C to B? This is 0 times SC of 1 and SC of 2. Can people call it out? Is there any water going from from A to C? No. So 0 SA of 1 plus, what is the water going from B? 1/2 of SB time 1 plus 2/3 of SC at time 1. So what do we have here? We have basically the system of linear equations, right? And we know that we can think about this now as the product of a matrix and a vector. And here these vectors are now, instead of representing unknowns, they're representing states. But this is where we'll pick up next time. And again, think about this on your homework.